Got it. And come back to Zoom and get the recording to the cloud. You could grab the light out of your way. All right, so let's do that. We've got this. I think all the buttons have been pressed. Welcome everyone on YouTube. Welcome everyone to the recording. All right. Welcome to the next Water, Wetlands, and Watershed seminar. Today we have two virtual speakers. They're introduced as just two dudes that like doing science together. So they're going to tell you a little bit more about that. We have Dr. Matthew Ross, is an assistant professor at Colorado State University. He's an ecosystem and watershed scientist, primarily interested in improving how to use data and models to better make environmental decisions, right? A lot of what we talk about in here. He hopes to accomplish this goal by building inclusive and welcoming teams and approaches that democratize complex data sets and tool chains. So you'll see there's a ton of data out there in the world right now. And if you can teach people how to go get it and use it, you can hopefully change the world a little bit. Similarly ambitious and idealistic is Dr. John Gardner, who I met 7 years ago in this room and I haven't seen since, or maybe at AGU, I don't know, but nice to see you again. He's an assistant professor in geology and environmental sciences at the University of Pittsburgh. He was an NSF postdoc fellow at the University of North Carolina and got his PhD from Duke University in 2018. He has a very small goal of wanting to know everything about Earth's rivers and surface waters, from how rivers meander and move sediment to why algal blooms happen. So luckily he's only 1 year into his career. He has a long time to, or into his professor, and a long time to work on that. His group, his current work works on using long-running global satellite imagery to develop databases of how rivers and estuaries change in size, shape, and water qualities. And with that, guys, I think you have control. So I'll spotlight you for the group and you can go ahead and get started.
Great. So I'll introduce myself and then John can take away for a bit. So John and I are going to pass this back and forth, but as Dr. Kaplan said, my name is Matt Ross, and I think it's just funny to do a collegial talk, and I'm really excited to do this with John, just because John and I have been working together on similar ideas since basically John started his PhD at Duke in 2014 when I was in my second or third year. And a lot of the ideas that you'll see here are really things that John and I have been passing back and forth for many years. And it's really exciting to see both the things that John is doing as those on his own, and then also for me to go on my own. And then it's kind of, we constantly circle back with each other, and it's just fun. And I encourage any of you doing PhDs or master's degrees, if you find someone like John, hold them dearly. They're great people. Okay, so John, go ahead.
And similarly, if you find someone like Matt, complementary skill sets here and interests. Yeah, thanks so much for having us. Y'all really create a fun seminar environment, even through Zoom. So thanks for hosting us. So we can just go ahead and
go for it.
You can go ahead and jump into it. Thanks for the introductions. If you want to go to the next slide, Matt.
Yep.
So I'm just gonna start off by stating some pretty well-known things, right? Rivers, lakes, surface water, super diverse. Inland waters are very diverse. All sorts of shapes, sizes, colors, chemistry, ecosystems, cutting across different land uses and climates and et cetera, which, inland water scientists, freshwater scientists, we have our work cut out for us. This is part of the complexity that we always he and haw at, like, it depends because this one's different, this lake's different than that one. But I think there's also a lot of opportunity in this inherent diversity, particularly when it comes to using remote sensing for discovery. And I'll circle back to that in a second. And of course, just these are such, I like to study things I like looking at. I could stare at these images all day. That's mainly what I want to do with my life. Next slide, please. And so in combination with that, like natural diversity that exists, kind of thinking about that as like a spatial phenomenon, right? Across lakes and across rivers. We also know rivers and lakes are changing, and perhaps more rapidly over the last 50 years than in the past. And right, this is happening in so many different ways, and there's too many studies to talk about. I can't can't mention them all, but I just wanted to cover a few examples of observational studies. So these aren't predictions of how we think things can change. These are things that we know have happened over the last 20 to 50 years. Right, we know stream flow regimes are changing, whether that's the magnitude or the frequency or the timing, right? Some areas are getting more extreme high flows or more extreme low flows, et cetera. And this is phenomena happening, all over the world. We know most lakes are warming, and this is from in situ observations. Right, that's a climate change effect, where stream flow regimes is all sorts of things, dams, climate change, et cetera. A more direct impact, we know most rivers are no longer free flowing, right? Whether it's dams or levees, about 77% of rivers are interrupted by something on their path from land to the ocean. And something we'll talk a little bit more today, I think Matt will talk about, is contrary. This is somewhat debated still, but we think most US lakes are actually getting clear. So there's a background of all sorts of like physical and chemical changes happening on top of this spatial diversity in rivers and lakes. I think putting these together provides a really, interesting challenge and opportunity for us to use remote sensing for. So you can go to the next slide, please. And so just thinking a little bit about remote sensing for discovery before we get into kind of remote sensing for management. Right, in my opinion, there's kind of like 4 different big categories of discovery that we can use remote sensing for right now. And these are ordered here kind of in like, I don't want to say the most easy, but the thing you can do most readily versus the thing that at the bottom, process from pattern, that takes more thinking. And we can do this because, as this figure is showing, this is just showing Landsat and Sentinel, showing that the swaths as they're covering the Earth, we're basically every time, the same time of day, basically, every 8 days for Landsat and every 5 days or so for Sentinel 2A and 2B, we're passing the same location on Earth in one big swath, getting both like a snapshot, you're covering the whole North America in about 6 minutes. Right, so you're collecting this spatial data, but also over time at even intervals at the same time, assuming you have no clouds, of course, with this optical data. And so the first thing you can do, particularly with Landsat, which the usable record for our purposes goes back to 1984, but there's earlier imagery, of course, too, is the immediate thing you can do is look at trends over time, right? Whether that's in, we're thinking about water stuff here. So this is an example of suspended sediment over time. So where data is sparse, because we have very few data relatively to the amount of remote sensing data in the spatial sense, we can get a trend over time in many, many locations. One step down, kind of adding complexity, we can look at some of the phenomenological drivers. So I say phenomenological because I think it's hard to get causal drivers from this kind of data because it is still limited compared to, a detailed field study. But taking advantage of these trends over time and maybe overlapping them with other data sets of land use, et cetera, that are spatial, you can overlap them and see where things overlap to get a sense of what could be driving these different trends in sediment concentration or whatever else you're considering that you can extract with satellites. Going down, even deeper, it can be really hard to make sense of data everywhere. So I think the opportunity here is, like we would design an experiment in the field, you can use this, the natural diversity of rivers and lakes that exist and the influences that, human and otherwise that perturb them to create kind of observational experiments rather than using all the data. Let's just pick the data along this elevation gradient or along this lake size gradient or whatever it is that interests you, and look at that response that you're able to measure. And then what I think is quite challenging moving, going deeper and even level I think there's opportunity to extract actual process-based information from pattern. And that's, following the ideas of landscape ecology. But we can do this also in aquatic systems, but this usually has to go with some sort of conceptual understanding of that process, or better yet, some sort of process-based model, of how water is moving, et cetera, and how it would create that pattern. So these are kind of, all broad categories I'm interested in. I'll be able to talk about a few of them today. But the one thing I wanted to say is all this remote sensing data that we'll be showing today is completely useless without field data, right? We'll never be able to replace the detailed process-based information you get from field data. And in fact, we rely on it deeply, which Matt will show some examples of how we're doing that.
If I can figure out how to go to the next slide. Okay, great. So yeah, John was emphasizing sort of what is possible with remote sensing, but one of the things that is sort of my particular focus with remote sensing is just making it easier to use this kind of data. So this is going to be a video based on a paper of mine. I have to mute it so I don't hear my own voice. Where basically what we're looking at here is anytime someone took a sample of these parameters, chlorophyll A, dissolved organic carbon, total suspended sediment, or Secchi depth, anywhere in the country through either federal or state water quality programs. So this is data from the water quality portal, and things flash when someone takes a sample. And we can see in the 80s, we weren't taking a lot of samples. We were taking a lot of sediment samples at that time. But if you flash forward just a little bit and go to 2010, you can see that we're taking a much broader array of diverse samples, both in lakes and rivers and estuaries. You can see particular regions like the Minnesota area, Wisconsin. There's a lot of lakes there, taking a lot of data. And then also Chesapeake Bay area. This is when you have really active Chesapeake Bay water quality monitoring programs. You can also see synoptic surveys and all kinds of other interesting patterns in here. But this data, as we know from lots of studies by Emily Stanley and others, is extremely biased because it's largely situated in large rivers. It's situated where people want to fund studies, potentially because of those areas are problematic. So now the next data set that's flashing over, this is Landsat 5, launched in 1984. And we're seeing sort of whenever those little squares flash and then in the lake or the river flashes, that's a cloud-free Landsat scene. And Landsat 5 alone had pretty good coverage, but it really starts to be more powerful when you interact it with other new satellites. So we had Landsat 5 here. Soon Landsat 7 will launch and overlaps with Landsat 5. Shortly after Landsat 7 sort of launched, it had some problems, but it's been going on for a decade. And then Landsat 5 went down. Luckily, we launched Landsat 8. And basically the idea here is that this data paired with the in situ data makes for a really powerful data set. And so for my postdoc with Tamlin Pavelski, we built this data set that we called Aquasat, which was essentially anytime you had a Landsat satellite passing over a water body that was visible to Landsat, because Landsat's resolution is 30 meters. So you really want water bodies that are wider than 90 meters on all sides for the very best. And so now what we're looking at is every time Landsat passed over and someone was randomly out in the field sampling, these little white flashes are when someone grabbed a sample on the same day, plus or minus a day actually, that Landsat passed over, and that goes into this data set we called Aquasat. And so now we have this matchup data set, which in machine learning land would be called like a labeled data set or a training data set. And this data set allows us to build models that take Landsat imagery, red, blue, green, near infrared, shortwave infrared data, and predict chlorophyll A, total suspended sediment, dissolved organic carbon. And this data set really makes it so that you can be a total field scientist and want to know if remote sensing data tells you something about your field site, your field lake, or something that back in the past, it just makes it a lot easier. It's always embarrassing when you see the like YouTube video like thing pop up. I love that. Get out of here. Okay. So we're just trying to make it easier so that you can take this data. And so it's just a CSV with all these matchups. So anybody sort of knows how to work with CSVs. If you've done some field work, you've probably used that. And then we built two critical other data sets. This data set was created by Simon Top, which is basically taking the deepest point of a lake, so the point that was furthest from any shoreline, and grabbing a stack of all the Landsat imagery for every lake. And so this is the number of lakes captured in these different little hex grids. And then this is on the right is the number of observations per lake. I'll try to get that laser pointer back up. So over here is the mean observations per lake. And then you can just see the total observations, and you can see basically when satellites launch and then when they sort of fall, and then other new satellites launch. And what this data set does again is every lake now, this is more than 52,000 lakes, has a stack of imagery from 1984 till now, where lots and lots of lakes have around 300, 340, 500 observations over time. And some have greater than 900 because they're in between Landsat swaths and they're getting captured twice. And we basically built a similar, almost identical data set for river data. This is one that John built. This is called River SR. The previous one's called Limnosat. We apparently didn't talk about name strategizing before we published this data. So on the top here, you see the true modal color of all these different rivers. And even just from this, you can see sort of patterns where you hit dams. So this is Colorado River and the Green River, and then you hit Lake Powell, and a lot of the sediment gets taken out of the river, and then it goes back down and it gets sort of more darker. And this is just a modal color as dominant wavelength. So this maps to how the human eye would see this. So we'll be talking a lot about color, but basically things in the 480, 500 range are kind of blue, 520 to 550 starts to get green, 550 to 570 is green and yellow. And those tell us about the sort of what's going on in the river. And again, this is a tabular data set. So anybody can download River SR. It links to NHD COM IDs. So that's the spatial component. So if you are used to working with a national hydrography data set, this data set links directly to it, but you also get a stack of color for every observation from Landsat. So just taking this sort of like complex remote sensing tool chains and democratizing them to make them easier for folks to use. And one of the primary folks who's used that is John and his team. Oh, you're muted, maybe, John?
Yes, I'm muted. Thank you. Matt and I are now going to go through a few vignettes of how we're each applying these different data sets that Matt just described into some science questions or some management questions. This was the challenge, I think, of designing a talk with two people, that there's actually lots of stories. So I apologize. We're going to blast you with a whole bunch of different stories. And in interest of time, I might skip a few things, actually. So yeah, I just wanted to first introduce the team. That a lot of the work I'm sharing these are the work of these 6 individuals. Thanks, Matt. You can go to the next slide. And so the big themes of the thing that we're working on are kind of like suspended sediment, in global rivers and estuaries. So from source to sink, channel change in global rivers, and river algal blooms, which Matt will talk more about. I'll mostly just be talking about some examples of our sediment work. Go to the next slide. And so just a flow chart of our basic approach that we're using for sediment, and increasing, expanding into chlorophyll, et cetera, is using the matchups that Matt described and feeding them through a very simple machine learning way of doing this. And in my opinion, this is kind of one of the few way forwards right now for inland waters, since we don't really have the high quality like field measurements and inherent optical data that oceanographers have. So we kind of have to, but we have tons and tons of field data from, that are embedded in Aquasat, from EPA, from USGS, et cetera, that we can kind of use the power of lots of data and lots of data cleaning to build these models. And so, the procedure, splitting your data for data that can use for training and data that never sees the model for validation. And we go through some automated steps where we feed it all the possible band combinations that have ever been used for sediment. And we let the model tell it what's the best band combinations to predict. The model does its cross-validation over different areas and times. This is at the scale of the US. And then we're able to then evaluate and validate that model based on the holdout data. And so this is an iterative procedure. As Aquasat continues, we can remake these models and hopefully improve them, and we can keep on pulling surface reflectance from lakes and rivers to then apply these models over. And then, pretty much with one click of a button, you get a very large database of suspended sediment or some other water quality variable that you could measure with optical data. And so this is just an example in the lower left corner of the current model that is the current algorithm, which is for the US. And we achieve pretty good error metrics for for an area that large, where often you're kind of limited to smaller areas when doing empirical data-driven models like this. And again, we're using this over Landsat 578. And so we can go to the next slide of how looking at some of the insights and some of the data that we get from this. And so the first thing I just wanted to highlight here is the spatial aspect of this data, as well as the temporal. So here we have 6 major US rivers. On the x-axis, we have the distance from the mouth, right? So the higher numbers on the left are more upstream. On the y-axis, the concentration, and then each line is a kind of your mean annual concentration profile along the river, right? From purple being older to yellow being newer. And so this is just tons of information in this figure, and the black triangles are dams, by the way, major dams. One of the things you might see is a suppressing of the profiles, right? And then when we do the trend test, right, you can see whole rivers are decreasing in concentration along the entire river. And when we add this all up, it's about 37% of US river miles have declining concentration from 1984 to 2018. And the other thing you might see are the spatial patterns, right? You might blur your eyes and see the overall downstream trend, or you might see all the wiggles from dams and tributaries, et cetera. But just thinking about the overall, the downstream pattern, right? We found that half of these large rivers that we can see with Landsat increase in sediment going downstream, which is kind of my expectation that like almost all rivers would, but it's actually only about half kind of have a statistically significant increasing trend downstream. Which is an interesting thing to explore what's going on there. And so I'm just going to talk a little bit more about why we might see that pattern, and then we'll dig into some more process information. So I was wondering, is this normal? Kind of like, should only half the rivers be increasing concentration downstream, right? As you are collecting more, watershed area and tributaries that could be contributing, more and more material. And so we don't have any idea of what rivers looked like sediment profile, since this is kind of a new data set, new way to look at sediment concentration along rivers. We have no way of predicting, but there is a global sediment transport model, WBM-SED, which some collaborators were able to run, Segi Cohen, in a simulation without dams. So we just took that data of what does the sediment profiles look like if we remove all the dams, and that modeled kind of like, quote, pristine situation compared to our observed trends. And we found that basically that a pattern of progressively decreasing concentration downstream is, about 2 or 3 times more likely in our observed data, right, with dams than this modeled kind of pre-dam simulation, which might be analogous to 100 or so years ago. So there's many other ways dams are contributing to this, and I can't discuss them all, but we're generally finding it's pretty much only the biggest dams that are really impacting this. And these 2 figures are just showing, right, 2 examples of rivers that reverse their pattern. One of them without dams was actually decreasing downstream, and for some reason adding dams a lot, it increased downstream. And the other is the Colorado River, which is one of the starkest example of that progressive decreasing of concentration due to those huge dams, where it should be just collecting tons and tons of sediment as you go. So that is kind of like the overall downstream trend, but I wanted to zoom in a little bit on all those wiggles on some work the student I'm working with is doing. And the student Rajaram Rajapati, he's looking at what about that recovery downstream of dams or lakes, really. Some of these could be natural lakes in some of these rivers, but focusing on the dam piece. Right, so here we took out the long-term mean annual river profile for two rivers, the Arkansas River and the Missouri River, just to highlight this, where all the red dots are dams. And so what he's basically doing is looking at that increase downstream of dam and seeing how many rivers recover their pre-reservoir concentration after a dam. How long does it take to do that, and how fast does that happen? And surprisingly, he's finding that a vast majority of river segments downstream of dams, like looking at about 110 of kind of the dams that had the proper data for, about 71% of these river segments are able to recover that pre-reservoir concentration. And on an average, it takes about 54 kilometers to do that, right? It can take anywhere from 0 to 700 kilometers, so the range is huge. And he's finding that it's, considering like, how can we figure out what processes are contributing to that? He was looking at, is it kind of channel characteristics and dam characteristics or watershed characteristics? And he's finding that it's probably more likely the river characteristics. In fact, like the dam type and basically how big of a reservoir impoundment does it make really matter, as well as how far downstream do you have of like a free flow length before you hit another reservoir. It needs time to recover. Right, and this is highlighting that maybe the in-channel characteristics are a little more important than like collecting sediment from the watershed to achieve this recovery. But this is still a work in progress. So moving on even further downstream. So what does, all of these spatial changes we're seeing and, declines over time and declines downstream mean for coast, right? We know that sediment, that's a pretty important thing that, for many years we found in the US and many other places of the world that have had a lot of damming, you decrease your sediment flux to your coast, which depend on that sediment to like maintain some elevation. And there's this great recent work by Evan DeChair that is finding generally sediment flux is declining kind of in the global north, that flux to the ocean, and increasing in the global south. And this is kind of due to the offset between wind dams happening and wind or major land use changes happening. But one thing that this work and many other work have typically focuses on is looking at that flux at kind of the most downstream non-tidal gauge. And so we're kind of expanding upstream and downstream, hopefully adding to that story, right? Filling in that gray space you see in that map, but also the last non-tidal gauge, there's potentially hundreds of kilometers between that and your estuary or your delta or your marsh. So we're also saying what happens in these tidal rivers and estuaries? What are the sediment concentrations? Are those decoupled from kind of what's happening further upstream in the watershed or at the watershed outlet? And so this is, from here on out, if anything I say, take with a grain of salt, because it's very, very preliminary analysis, where the other things before are, becoming more finalized. This is work by a student I'm working with, Poonwak Prum. And so he's looking at, 110 US estuaries in Alaska and US right now, or right in this pie chart, just looking at the estuary overall, what's kind of that estuary-wide concentration? Is it increasing or decreasing from 1984 to now? And he found about 60%. So this pie chart shows the number of estuaries rather than the percent. So if you add it up, it's about 56% of estuaries in the US and Alaska are decreasing in concentration, right? It's a pretty significant majority. And a small percentage are actually increasing, and those are almost exclusively in Alaska. Right, but this is only part of the story where showing one example, since we have this benefit of having this spatial data, and we get look at trends, to pretty high resolution within an estuary. This map on the right shows some preliminary data from the Chesapeake Bay, where everything in red is a location with a decreasing concentration. Everything with yellow, there's no trend, and everything in green, there's an increasing concentration. And so we're starting to tease out maybe what do these spatial patterns, are these important for, for the long-term sustainability of marshes or wetlands in coastal areas. And so that we're just starting to develop this data and figure out where that goes. Can move on to the next question. And so I'm only going to just quickly touch on this, but right, the sediment, of course, these measurements that we're making are also highly linked to how river channels themselves are changing. Right, the general thought from some work in the Amazon that has, really nice free flowing rivers is that if you increase sediment concentration, whether that's due to deforestation or something else, that you would actually increase your rates of meandering as you get more deposition and erosion happening. And so we're starting to link our data sets, but this is work from a postdoc I'm working with, La Dente. And so he's creating basically annual center lines from 1984 to now. And with those center lines at a very, very high resolution, he's able to estimate all of the change in position. And so rather than meandering, I'm just calling this channel change because, right, not all rivers are meandering. So we're measuring channel change, shifting of where the channels are in braided rivers and meandering rivers and anastematizing rivers. And we're doing this globally, but we're have a study focused on the Amazon right now because it's if you can get our workflow working here, it can kind of work many other places. So some very, very preliminary results is we're finding that in many places of the Amazon, meandering rates rates of channel change are increasing. And, and in some places, this is linked to increased what we're calling river deforestation, where that river meandering, in a forested area like this is working the floodplain and actually removing trees. And so in many of these areas, we found this river deforestation is actually increasing over time, Amazon-wide. And while we compared it to the overall deforestation, right, stuff that people are cutting down or wildfires or any other reasons that forest is removed. And while it's a very small percent, it's almost tripled, over the last 40 years that there's about 1 to 4% increase from about 1 to 4% of all deforestation in the Amazon is caused just by natural river channel change. And so lastly, I just want to sum up with some future work that is, go to the next slide, Matt, of stuff we're expanding into and to look out for. Of course, these, we want to make these products and make them available to everyone. But these are mainly, I would say, kind of academic products, may not have the accuracy for management. But hopefully this suspended sediment product for the US will be out soon, and we're expanding this globally. So this is an example of, the initial database of river surface reflectance, just showing color kind of like binned into 3 different groups, right? Seeing of course, the prevalence of yellow rivers everywhere. likely due to sediment. So at the scale of these rivers, we're working on, these are all the locations. These are the SWAT rivers, the surface water ocean topography river database. So we'll have a sediment measurement, for each one of these river reaches, average over the entire river reach for each Landsat and Sentinel overpass. And we'll hopefully be making an operational product will actually be paired with SWAT discharge. So we'll have some ability to look at sediment flux through all these rivers. And that'll only, though, be from satellite data from 2013 to the future. But we're continuing kind of these more less accurate academic products over the whole Landsat record. As well as we'll be hopefully expanding our US estuary work into suspended sediment data products for global estuaries, as well as these global annual river center lines to look at channel change. And so I've mostly talked about rivers here, and now Matt will be able to talk about some other data vignettes and stories, focusing a little more on lakes.
Thanks, John. So yeah, John was really focused on the sort of river side of this, and I'm going to switch over to using this LimnoSat data set, which is lake oriented. And again, it's just 50,000 lakes. On average, they have more than 300 observations of lake color from Landsat. So the case study I'm going to focus on is water quality change in the Western US. This is actually work mostly led by Bella Alexa, who's going to be a professor at CU Boulder soon, and Sam Sillen, who now works in John's lab when he was doing his master's with Sarah Collins at University of Wyoming. And my former master's student, Miles Austin, did some of this work. So the idea here is that there's a pretty heavy bias in a harmful algal bloom research towards places where harmful algal blooms have been a historic problem, like dear old Florida down there in the southern part of the country, because that's where people have identified this as a problem, either for drinking water or for other reasons. Harmful algal blooms are basically when you have too much algae or a cyanobloom. It's a relatively poorly defined term, but it can have ecosystem effects and effects on human health, drinking water, taste and odor compounds. And you can just see in the middle of the country, there's just a lot less harmful algal bloom publications. Again, this is work by Sam Sillen. So the idea is that we were going to use LimnoSat to really study this sort of quadrat of high elevation states: Colorado, Utah, Wyoming, Idaho, and Montana. And this was inspired by this increasing trend in harmful algal bloom advisories in both Wyoming and Colorado. So Sarah was working in Wyoming on harmful algal blooms, and I was working in Colorado. And then we met and talked, and we're like, hey, let's just do this together. And both states have this increasing trend of basically their state agencies giving an increasing number of warnings that algae blooms are happening and they're problematic, and don't swim in this lake or stop taking drinking water from this lake. So you can see this pretty clear trend in advisories. I apologize, the train is running by if you can hear that. I certainly can. And there's reason to think that, hey, yeah, algae blooms are increasing everywhere. There's this paper by Jeff Ho and others that shows widespread global increases in intense lake phytoplankton blooms since the 1980s. So this is a big global data set where they sort of suggest that maybe algae blooms are increasing, but then other work by Grace Wilkinson and Simon Topp and others has shown that there's actually no evidence of widespread algal bloom intensification in hundreds of lakes in the US. And that's based on in situ data, where they sort of show that it's just not changing all that much. So we wanted to sort of like try to resolve this in the Intermountain West, but we know that long-term records of in situ data are rare. So this is just yearly data in Granite Springs Reservoir, which is one of the reservoirs that has had an advisory recently. And basically there's just not that many observations. If you only used, sometimes someone went out there and measured algae chlorophyll A by hand. And we know that most of the lakes that we measure stuff in are biased towards larger, more charismatic lakes. So here is just a plot from Emily Stanley's paper in 2019 showing the area of observations and then the true area of actual lakes. Basically, just there's a lot more small lakes that we don't observe with in situ data sets. So remote sensing can really help us out. This is the same Granite Springs Reservoir with in situ data, and then this is the yearly Landsat observations of that reservoir. So if we can turn those Landsat observations into predictions, can be really helpful. like in states like Wyoming, where there's 518 lakes that are visible. So the first step we did in this, as John has done as well, often when we get these stacks of imagery over these lakes, or rivers, the first thing we do is look at color. So to have a change in algae bloom status, you almost certainly have to have a change in color. Like if a lake is oligotrophic, it's probably pretty blue. And if it's eutrophic and has a lot of algae blooms, it's probably pretty green. So we took a look at this in a paper led by Bella that got published in ERL recently, basically showing that most lakes have no trend in color. Some are getting bluer, so they were already blue in the past, and now they're getting more blue, which we think of as like more oligotrophic. Some are going from green to blue, so they were maybe eutrophic, and now they're getting more oligotrophic. Some were going from green to more green or yellow, so they're getting green or brown, and some were blue and transitioned to green. But the majority didn't change, and these two trends of intensifying green versus intensifying blue kind of balance each other out. And we show that there's no real spatial trend to this, although it is consistent with some of Simon's work modeling Secchi depth, so water clarity, showing that where lakes are getting bluer, it tends to cluster around urban areas, which we attribute to the Clean Water Act being pretty successful, changing, at least in urban areas, water quality for the better. But of course, this is just looking at color. So the next step that Sam Sillen led was to use remote sensing. It's basically the exact same modeling approach John highlighted earlier. We use all these various data sets: Aquasat, Lagos US, Lake Cat, which gives you a bunch of lake catchment variables, and climate data from Jared Willard's recent paper that predicts temperature in 180,000 lakes since 1980 on a daily time step, which is an amazing data set to use. And then we use that in a training data set, and we try to predict the categories of the lake. So is it oligotrophic, which is 0 to 2.6 micrograms per liter chlorophyll A, mesotrophic 2.6 to 7 micrograms per liter, or eutrophic greater than 7 micrograms? And this is based on National Lake Assessment Trophic Status Index data. And then we use a gradient boosting model, which is based off of Simon's code and a little bit John's. And basically that data set goes through and it tries to figure out what predicts these the status of the lake most accurately: oligotrophic, mesotrophic, or eutrophic. And mostly what we see in our model results is that the variables that are either optical or climatic are the most important. So the green to blue ratio is really important: mean 14-day temp or wind speed, and then the rest are optical parameters from Landsat. And with that model, we get an overall accuracy of 71% predicting the status. So we're pretty dang good at predicting if a lake is actually oligotrophic. So on the x-axis here is the truth, so the sort of observed, and on the y-axis is our remote sensing estimates. That's the predicted. And we do a pretty good job predicting oligotrophic, but we do get confused between oligotrophic and mesotrophic. But between oligotrophic and eutrophic, we're a lot better. We have very few times that we predict that it's oligotrophic when it's actually eutrophic. So overall, we thought this was good enough to move forward and do some science. We had more than 600,000 observations in the Western US of 1,000 lakes, and we sort of take each lake, and each lake we categorize into this kind of data. So basically, this is the number of observations per year that it was categorized into each one of those oligotrophic, mesotrophic, or eutrophic categories, and then we're looking for change over time. And again, most of the lakes, as with the color data, shows no trend, which basically just means it was a lake like this. No, it was blue in the past or oligotrophic in the past, and it's still oligotrophic. And there's no real change between these two time periods of 1984 to 2005 and the more recent 2005 to 2020. We see some that are getting more oligotrophic, so bluer. So this, if you compare this, there's just a lot more green eutrophy on the left side and more blue oligotrophy on the right side. And a smaller percentage are going from being blue to being green. And this is a sense of the intensity of the change. So on the x-axis here is the change in the percent oligotrophic. So how many more lakes switched to being oligotrophic, or sorry, not how many more lakes, what percentage of the year were they categorized as oligotrophic? So this is a lake that has a really big shift towards oligotrophy. And then we had the lake on the right-hand side here is a lake that has a really big shift towards eutrophy. And to sort of summarize that, the majority of the lakes were not trending. Again, this is really consistent with the color data, which is what I would expect. 19% of the lakes are becoming more oligotrophic, and it's hard to see, but a lot of these are sort of clustered in urban areas where they're getting more oligotrophic. And only 3% of lakes are becoming more eutrophic. So we sort of attribute this to basically like, even though advisories are increasing, a lot of strong evidence, both from Simon's paper, Sam paper, Grace Wilkinson's paper, using different methods, is suggesting that actually that's mostly a perception, and is probably because there's more attention about the impacts of harmful algal blooms, which is this nice paper that there's a perceived global increase in algae blooms. It's attributable to intensified monitoring and emerging bloom impacts. So the impacts are getting worse, and so we're noticing them more. And this is basically consistent with other papers, and we like to highlight this, that basically there's a lot of increasing evidence that in the US at least, there's improving water quality in lakes, in some lakes at least, over the last 40 years. So just taking this idea and moving forward, I'll briefly talk about some of our new work. I'm not going to click on this website, but in my lab, we have a whole new team of data scientists, PhD students working on some of the work I'm about to talk about. And we're hoping to move to remote sensing as part of a daily water quality estimate. So the problem with remote sensing, if you're in a cloudy region, you kind of have to wait for the clouds to clear in order to estimate water quality. So we want to use remote sensing as part of a larger model that can predict daily, even where remote sensing is just a part of a bigger model. We want to use this data to help managers make better decisions about their reservoirs or lakes or rivers. And we want to do some integrated river reservoir studies. So what am I going to do? I'm going to talk about this really quickly. This is Colorado. This is the Colorado Big Thompson project, which takes water from the upper Colorado River here down in the bottom left, pumps it through these pink tunnels to the Front Range where all the people live. And then these are the major water supply reservoirs that feed water to Boulder, Loveland, and Fort Collins. And basically, if we take this data set, right now they don't have an operational use of water quality estimates to make pumping decisions. So when does water get moved from the west slope to the east slope? And this is getting to be really important to use water quality estimates in decision making, because in 2020 we had these massive fires both on the west slope and the east slope that's really impacting water quality in our water supply. So the proposal that I recently got funded with NASA to do is basically to say, all right, let's abstract out this system and make all the now black circles are reservoirs and red arrows are canals and tunnels, and the arrows indicate where they have pumping. They can make decisions about, are they pumping left and right? And then there's also river connections that they have less control over. And then they pump across the Continental Divide to all the source water supply reservoirs here on the right-hand side. And basically the idea is that the way the system is now, you could have a bloom that starts to occur maybe on Tuesday, and this is just totally made up. This has not happened. But you could have a bloom that's starting to occur in this little reservoir on Tuesday. And because pumping operations were spreading at a normal rate, you start pumping over to the right-hand side. Your existing observation platform doesn't observe the bloom, so you're not changing decisions because you can't see, because you're either downloading sensor data or taking grab samples. And then you start to spread this algae bloom to other lakes, because you're maybe spreading high nutrient, high algal biomass water across the divide. And then you finally, Fort Collins detects a bloom when they're trying to treat water for drinking. And this is in contrast to where if we had this decision support system that's an integrated remote sensing modeling product, where we would be identifying, hey, you might have a bloom, go take some samples, check if you do, and then they stop pumping, and that isolates this bloom among this family of reservoirs. So that's sort of this idea that's just getting started in my lab. Really similarly, John and I are funded recently to work on a unified project in the Illinois and Ohio river basins. And basically, we know from collaborators in remote sensing of color that these areas in the Illinois River, these are Landsat swaths in gray, and this is in green is the remote sensible river. These rivers experience algae blooms that interrupt the ability for both people in Illinois and Ohio to have clean drinking water. And so John and I are funded to look at the impact of reservoirs and sort of lake connectivity to that causes algae blooms and causes their spread throughout these river networks. So this is happening both in the Illinois and the Ohio. The Ohio River is a little more complex. You have much larger tributaries coming in, but on the left here is these color, where basically when you're in the green area, it's much more likely to be a bloom. And John and I are just getting started to look at that and convert that into chlorophyll A estimates. Again, using that sort of daily model approach. Some conclusions or hot takes. I'm not sure these are that hot of takes, but one of our goals in working in the way we do is that we want to make our remote sensing data much more tabular. So just sort of something that more people who work in the field are able to use. So we think that makes that more inclusive and makes working with remote sensing more democratized. We think having a bigger community that uses remote sensing, it makes for better science. We're really excited that the USGS and others are funding Aquasat version 2. So we're going to make a much better version of that. And build on some of the work that John's already done. I would just also highlight that this field is really rapidly changing. NASA's working on a global pixel level water quality estimation platform. There's a new Landsat aquatic reflectance product, which will make our models even better. And then I also would just say that managers really want to integrate remote sensing into their decision process, but they're not quite sure how to do it. So if you're interested in a career in sort of management, I know one of you is a business major in the room. I think this notion of connecting remote sensing estimates of water quality to management and business decisions is actually one that people on the sort of utility municipality side are really excited about. So with that, I think we'll just, I think we took over the entire time. So if there's any time for questions, we're here.
All right, well, let's give a round of applause to Dr. Ross and Dr. Gardner. A really cool talk, a lot of examples, a lot of vignettes. And so, yeah, if you have to run to class, you can, but otherwise we'll take questions from the room and I'll check for questions in the Zoom and on the YouTube. So I know Dr. Clark's got a question. I'm sure he does back there.
Yeah, so I'm curious. I mean, just wonderful talk, really amazing what you all are doing to integrate that on the ground sampling with remote sensing and how that can really expand our ability to kind of look across the landscape. But I'm kind of curious from the standpoint of the time frame within which we're observing these changes and declines or increases and whatnot. Any feeling for how that may fit in the broader context? Like, I mean, if you magically could look back further in time, did the 1980s, 1990s kind of represent some sort of a peak in transition of things like sediment loading or nutrient availability? And so we're kind of looking at a recovery from some point, or is this, kind of representative of maybe a longer term trend?
Yeah, I think on the lake side, it's a really interesting question to think about. Was like the 80s and 90s the worst? And then Clean Water Act amendments really started, because those were, even though that was passed in 1972, a lot of the improvements to wastewater treatment plants and taking phosphorus out of detergents and all that stuff, that was phased in over time. So I think it's actually plausible that you're right, that sort of mid 80s, mid 90s, early 90s might have been sort of the highest nutrient loading and therefore potentially the sort of greenest. The problem is chlorophyll A remote sensing is sort of really dicey with Landsat 5. That's why we did that oligotrophic, eutrophic, mesotrophic, because it's just not, it wasn't built ever for water remote sensing. Landsat 8 and 9 are they're a lot better. They have some bands that really help out with that. So they have an aerosol band that helps be more precise about the atmosphere correction. And so going further back with in time is kind of harder with the lakes. John and I haven't talked about this actually, but as a handoff for John to talk about sort of dams and sediment, I do think recently USGS has put a lot of effort into making Landsat 4 more useful. So it's a totally different sensor than Landsat 5 going back to 1973, but there are quite a few papers from 1973 to in the mid 1980s that you can do reasonably good with sediment. So I haven't talked to John about this, but if there's any, I think it's plausible you could do an okay job doing some more sediment or even Secchi depth going back to the 70s. But that sort of effort by the USGS to make that data more useful was after we had built all the Aquasat stuff. So the next round of Aquasat, we're talking about if we want to include it to go even a little bit further back, which would be nice because then you're right at the cusp of Clean Water Act sort of happening. But on the dam side, it's a very different story. So I'll let John kind of hop in on that.
Yeah, for rivers and dam stuff, course, like we reached peak dam in the US in like the 60s. So there's, unless you have you're never going to be able to get like the full change in a remote sensing data set. There's like maybe like there's 9 stations that have a record longer than 50 years in sediment in the US. Those are all in Western rivers. That's one of the motivations to do some of this work globally, because you can make some inferences, because dam development and land use change has happened in different temporal separations around the world. So you can start to, I feel like, draw some inferences by kind of using all the rivers as your laboratory to design that experiment. Like, for example, like right in China, all the land use change happened hundreds and hundreds of years before it happened in the US, but their dams have kind of all happened the last 20 years. And like, right, the relative timing of the land use change in the dams is kind of the story when it comes to rivers and sediment. And you can just take advantage of kind of the way different regions have developed to maybe infer some things about that.
Yeah, no, thank you. It's still amazing work that you all are doing, and to make it a more hands-on and useful tool for managers is really neat to see. Yeah.
So for the folks on Zoom, I got students on here for Hobmosen and Ashley, have any questions? The black box muted Zoom, it's okay. I want to ask, like, obviously, we have a lot of folks in the like geosciences, there's a commitment to open data and things more and more nowadays, but the work to put together, like, I can't remember all that, you have different names, there's like Aquasat and they're like, these huge data sets that are you couldn't even begin to imagine all the things that people might do with them. So it's very compelling to publish them and make them open and On the other hand, it's like, man, it was a lot of work to compile them and put them together. And I've got like 17 things I can imagine that I want to do with them. So how did you guys decide to just let her rip and put it out in the world, given like, just career challenges and, the goal of producing all, from that intense investment that you made? You're muted, but it's look very thoughtful.
Yeah, so the open science side of this, I think it's just like a really important mental shift that I don't know when I made it, sometime in my PhD. Emily Bernhardt was my PhD advisor along with Martin Doyle, and she had been making this transition from really like working on a lot of like local sort of data sets that you publish if you can, but it's not a huge important part, to working on these huge syntheses where enabling the community was like the proposal in a lot of ways. So like her
Pulse and things like that.
Stream Pulse, and now Macrosheds, which is a project we work on together. And so when I was working with Tamlin, I was not a remote sensor, and I wanted to make Aquasat for me and Tamlin's group and others, but I also knew I'm not a remote sensor. And so actually that one was a lot of like, I'm going to try a thing, but I want some feedback. And the best way to do that is to just be like super open science oriented. And so I think there's two mindsets that shift. One is the scarcity mindset. If you're just like, look, no one cares about whatever question you have. There's a billion questions out there, and no one's going to sort of like scooping is very, very rare. If you have that mindset that like no one's going to scoop your idea, because in fact your idea is so contingent on your history and the way you'd approach it is different. And that if you drop that and you're like, great, then this data set's everyone's. And then if you also feel a little bit insecure about your approach,
It's
like
perfect.
then you publish your code in an open way and you publish your data in an open way, then you have all these people telling you what you did wrong. And if you did it open, it's lovely, because that's part of the process, is like, oh yeah. So when we're thinking about Aquasat V2, a lot of that's based on people in Mexico and China and other places trying to use it and being annoyed with decisions I made on the first one. And I'm like, I so appreciate your email. I'm going to reach out and do a better job next time. And so that version of science is so much more fun to me, where you're just open to knowing you can't do it right the first time. And that's why, I think the other part is like, these data sets, when they're better, I think they could be a lot better. I think, I meant to say Bella and Sam did all of that work on the lake color stuff in less than a year. And I think that's because it's just like so much easier to work with that data. But I think as they get better, it should be like just reducing that time to innovation for others, to science, to asking science questions with remote sensing is really where we want to go. And like, that can't just be John and I'm heavily, and I know John is too, invested in the infrastructure side. Just like, I hate the notion of really smart people banging their head on dumb things that I've already banged my head against. So trying to like make it easier. I think that's where that comes from. I don't know, John, if you had some other thoughts.
I have nothing to add on the open science stuff now.
Yeah, and it was sort of, I was kind of queuing that up for more for the students, and the ones in the room all jetted. So
Yeah, sorry, it's we.
Okay.
Yeah.
It'll live on the YouTube, so that's good. I appreciate that that look at that philosophy. So, any last questions? I think we'll wrap it. Thanks. I really appreciate you guys speaking with us, and look forward to hearing more from your groups, which seems like it's not going to stop anytime soon. So, thanks a lot.
Thanks so much. That was really fun.